Um, Anybody walking by, if you hate ferric chloride, this is the presentation for you. Ferric chloride, bad. Yes, this is the place. Okay, I'm going to introduce to this classroom a way to activate a ubiquitous residual steel slag that's left all over the country into a paradigm for nutrient. Do you hate ferric? You should come into this. For nutrient removal, particularly in the anaerobic digestion process, but for all wastewater. So I'll introduce you to this material, show you how it can be used as an alternative for conventional coagulants, ferric and alum, not just ferric in this case. We'll talk about iron, show its place in a sustainable cycle, and then lastly I'm going to turn it over to my colleague John Teaford to discuss an unanticipated benefit, how this works for dewatering. So let me start with a brief description of this. If I were to try to explain it to my senator, I would say it's a moon rock, and it kind of is. It's a byproduct from steel, and it's easy to mill. So whenever you have a steel plant on your right up there, the blue dots on there, the dark blue dots are locations of large steel making facilities in the United States, and the light blue dots are wastewater treatment plants above, I think 10 MGD is the cutoff there on that map. So you can see distributed throughout the United States, particularly near the major metro areas, are large steel making facilities, and wherever you have those, you've got mountains of this material. And it otherwise just stays there and builds up. It's easy to mill. The favorite adjective we have with it is we can grind it to the fineness of pepper, and that's actually how we apply it in wastewater treatment plants. And I'm going to show you how that's done. This session is about sustainability, and that's what drew us here and drew us to actually use this material in a potent paradigm to basically immobilize nutrients in anaerobic digesters. And that word means a lot of different things to a lot of different people. So I'm going to use it in the classic sense in terms of its chemical benefit and its economic benefit, cradle to grave, just by simply adding this material to anaerobic digesters. And then we'll talk about some unanticipated benefits, dewatering being among them. So I've been studying this topic for almost 30 years. I've been a researcher and an engineer trying to improve anaerobic digestion processes, and I've been shopping for something to replace ferric chloride and other conventional, expensive, and dangerous chemicals. And in doing so, we did some research on using milled steel slag fines to improve phosphate and sulfide removal and basically displace these expensive chemicals like iron in this process. And this stuff, it doesn't have a sexy name, steel slag, but as I showed you earlier, it's cheap, it's abundant, and it's available, and it's distributed worldwide. So for every ton of steel that's made, you get about 15% by mass steel slag. And it's easy to mill into a useful reagent. And I include this picture to just kind of give you the scale for how this stuff is stockpiled at steel plants all over the world. And it's literally, you can't use it all. And right now it's just used as a cheap episodic construction aggregate. That's pretty much its only use. So that's why these piles build up wherever a steel plant are. And even if we use tons of year, we would never run out. So there's no magic to this. When you make iron or reagent grade steel, you discharge steel slag, and this is its composition. It's inert stuff. It's the consistency of activated carbon. And you can mill it to whatever size you want pretty inexpensively. And you can see the major ingredients here: iron, calcium, and silicon oxides. The stuff is incredibly stable. But what's great about it is it's an excellent sorbent, a lot cheaper and a lot easier to deal with than activated carbon. And then one side benefit that we found, not anticipating this, is it's got a fair amount of free lime with it. And that free lime is a benefit. It dissolves in anaerobic digesters and gives you a little bit of alkalinity. So along with this very sorptive iron oxyhydroxide, the Fe2O3 up there, and the calcium and silica, this chemical profile basically grabs phosphorus, phosphate, sulfide, and siloxane because of that chemical profile right there. So that's what really attracted to me to this stuff. It's very stable, high sorptive surface, has a little bit of alkalinity, and a really great sorption profile. So what we did to test this was at a real treatment plant with real digester sludge. We added steel slag that was ground. This is basic oxygen furnace slag that was ground pretty finely. And I'm going to show you some results that show this in an operating digester at steady state at a pilot scale, 100 liters. On your left up there is the free orthophosphate. On the right axis is the percent of phosphate removed. And you can see right in the middle there's a nice straight line. And that's the sweet spot. So we can show a dose response for this in terms of grabbing orthophosphate and controlling free phosphate in the digester liquor. And the sweet spot's between about 1 and 10 grams per liter, and we can really knock out phosphate down. So we're talking about something, a fraction of the size of aspirin in terms of volume in a liter of digesting sludge. So it's not very much, can have a profound effect on soluble phosphate. The same is true, and concomitantly so, with sulfur. So it removes phosphate and hydrogen sulfide, or its precursor, sulfide, any sulfide-containing species, in about that same dose response range. So very little added in an active digester can immobilize both soluble orthophosphate and any sulfide-containing species that produce hydrogen sulfide, the bad stuff that we don't want, and the biogas, the stinky stuff, all at the same time for just a little bit of dose, about a gram to a couple of grams per liter. Okay, now I'm going to start bragging about the alternative, which is what we add to digesters now, and that is ferric chloride, either reduced ferrous chloride or ferric chloride more commonly. And the problem with this stuff is it eventually turns into a scaling agent. So yes, it's potent, yes, it grabs phosphate, yes, it coordinates sulfide, but it's got some other bad side effects. And those side effects usually manifest in Vivianite scaling, and it's because we're adding a liquid. And what that liquid does is turn into a scaling agent and eventually builds up on pipes, and we've all seen the horror stories associated with that. The other downside of this is it's a dangerous liquid. It's an acidic liquid. It has to have special handling characteristics, and it's very expensive, much more expensive compared to a solid phase sorbent in terms of this stuff. So when you add a solid, you essentially immobilize this stuff right out of solution. It doesn't have a chance to adhere to a pipe wall. So you avoid scaling when you do this. And basically the story is when you add this to an anaerobic digester, what happens on slag in solution stays on slag. It's like activated carbon. The magic happens in solution. There's no chance for this to cause scaling at all, at least in theory. And so whether it gets in the heat transfer equipment or not, we don't have the possibility for scaling like we do with iron chloride or other liquid reagent chemicals that eventually turn into solid. This stuff is already solid. So there's no scaling potential with it at all. So in a sustainability construct, we're not talking about recycling. What we're talking about is upcycling. We're taking something from another industry that's a waste product that's stockpiled, bringing it into the wastewater sector, and then looking at it in terms of cradle to grave. And the grave is actually land application. This stuff is inert, so we can have a sustainable outcome here. So we'll take a waste product that's stockpiled, introduce it to the conventional wastewater treatment process, and then it goes on to Latin application literally as a phosphorus and sulfur enhancement. So the common questions that we get in the sustainability context are the following. Does it pass a wet test? The answer is yes. We've done both 503 and flow-through wet tests with microorganisms, including algae and immature fathead minnows. Passes TCLP, no problem. You can throw acid in it. It's very stable. It won't leach. And then lastly, more recently, the questions that we've been getting around dewatering, and it does have a dewatering benefit. And for that, I'm going to turn that over to my colleague, John Teaford, who's going to explain the dewatering side of things.
Thank you, Mark. So a question that we got from one of our early customers was, what is the impact that this material has on our dewatering operations? That customer used ferric chloride today, and they imagined or believed that their ferric chloride was having some positive impact on dewatering. They didn't know how much, but they thought there would be a positive impact. And so they asked us to show them, if we stop using ferric chloride and start using your material, will we have some additional expense in dewatering, either through additional electricity for running centrifuges for longer or additional polymers. Dewatering can be sometimes 4 or 5 times more expensive than phosphorus and sulfur removal for a wastewater plant. So that was an important question to answer. To answer the question, we operated 4 test digesters. You can see them up here on the left. Those are 4-gallon test digesters that we ran continuously for, they've been going now for about 8 months. In the middle, you see some of the test apparatus that we have. The test that we conducted was a time to filter test. So in this test, we took a Buckner funnel and we placed a paper filter on top of that. We added our digestate onto it and clicked a stopwatch and timed how long it took the liquid material to flow through the funnel into the graduated cylinder below. So that was how much time did it take water to pass out of the sludge. And we did that for our test digesters, which there was one was a control, one was ferric chloride dosed at 200 milligrams per liter, one was our steel slag dosed at 3 grams per liter, and one was steel slag dosed at 6 grams per liter. And then after that, we wanted to answer a question of, is there a change in the weight of the material, the sludge at the end of the day? If we're adding steel slag, it's a heavy material, does it change the weight of the eventual biosolids when it's compared to ferric chloride? So to answer that, we took the sludge from our ferric digester and the sludge from our test digesters, and we dried them out overnight till they got to 0% humidity or moisture content, and then weighed them to see if there was a difference in weight. And these are the results. So the left axis for those orange bars, that's the time to dewater. That's how many seconds it took to dewater, or I guess minutes, to dewater the ferric chloride laden sludge. Took 30.8 minutes to dewater on average. The steel slag at 3 grams per liter took 14.4 minutes, a little bit less than half the time. And then slag with 6 grams per liter dosed was a little bit faster than that even. So we got a dose response there for the time it took the sludge to express water out of it. And then on the right is the weight that we talked about a moment ago. On the left axis, that's the mean total solids percent. And for ferric chloride, it came out at about 4.1 TS percent, and slag at the 3 and 6 grams per liter were about the same. There was not a real difference in the weight of the material. So the message there is that ferric chloride is a heavy material. It weighs a lot too. It's basically liquid iron, and it neither of our materials have a distinct difference between them on the weight of the resulting sludge that comes out of a digester. So a plant doesn't need to worry about trucking more weight away. And while we were doing that testing, we also looked at we redid our phosphorus and sulfur tests. So on the left for the orange bars, that's the phosphate in milligrams per liter. Control digester 800, ferric chloride knocked a good bit of it down. And then slag at just 3 grams per liter knocked it down to 100. That's a much larger percentage removal. So ferric chloride there again was dosed at 200 milligrams per liter, and the slag at 3 grams per liter outperformed it substantially. And then we repeated the soluble sulfide test. On the right, the green bars, the left axis is sulfide in milligrams per liter, and we showed that ferric chloride reduced sulfide a little bit from the control. We think that if we had left the ferric chloride in contact with the sludge for a little bit longer, it might have had more of an effect. We think ferric chloride probably takes a little bit longer than slag to have a reaction. But our slag-dosed digesters got that down to undetectable levels. So the lowest level we could detect with that test was 0.1 milligrams per liter, so it's something less than that. We got almost all of the sulfide to attach to the slag, which means, of course, there's not as much odor in certain parts of the plant. It also means that there's much less hydrogen sulfide created. And so just to prove that that soluble sulfide translates to hydrogen sulfide reduction, we repeated that test in the gas phase, and we measured how much H2S came off of those different samples. And for the control, we had 150 ppm. Ferric knocked it down to 99, and then our two slag-dosed samples knocked the H2S down very dramatically. So that means less sulfur scrubbing. It means less H2S is ever formed to impact the pipes. Sulfur scrubbing material will last considerably longer. So as we now imagine what this looks like as it goes into a wastewater treatment plant, we're installing our first equipment now, and that's going to go into a 7 million gallon per day wastewater treatment plant. We're going to deliver it in super sacks. So those will be 2-ton super sacks. They'll be hung on a bulk bag unloader, which you see in the middle there. That's a piece of equipment that stands 5 or 6 feet wide and maybe 10 or 11 feet tall. Takes up a pretty small footprint. Costs about $60,000 in total capex for that piece of equipment. And then on the right, we're going to enclose this one in a small temporary building, just to keep it out of the weather. And we add that material somewhere upstream of the digester. So in this case, it's going to go between the primary clarifier and the gravity thickener at this plant. It can go into a primary clarifier, which is a great way to settle it down and have it injected into the anaerobic digester. It can go into a digester itself if that digester is available, or into a mixing well. Then it goes through dewatering, and it eventually flows out the door. However the plant manages their biosolids, it's a great contribution, as Mark mentioned. It works for landfill or for land application, and it probably also works for incineration if you happen to do that. It's already been through a steel mill. It's been plenty hot. So recapping on the benefits that we imagine from this process, it is as effective as the chemical treatment that we're replacing. We showed you the results there. It's environmentally beneficial to reuse an industrial waste product, to upcycle it and beneficially reuse it. It's less expensive than the chemicals that are used today. It accelerates the dewatering process, and it reduces scaling in the form of struvite. You'll get much less struvite in the plant. So, we'd like to thank the folks at CU Boulder, Mark, and the rest of the team at the University of Colorado. We've got Chris Iman and Amelia who helped us with some of the research. The Boulder Wastewater Reclamation Facility, Sarah Fox from HDR did a lot of the testing. We had HDR come in and do a lot of the testing for us, and venture partners at the University of Colorado. So thank you very much, and I'd be happy to answer any questions.